Okay, so on today's lecture, we will continue our talk about point processes, and today we will define a point process more precisely. So it's all mathematical statement and definition. So on the previous lecture, we saw some examples of a point process, and I assume you have such a picture that a point process is some random collection of a point of points in the space. So we have some space. You can imagine that this is RD. For example, this is the most simple case, but nevertheless, it is rather general. So a point process is a random collection of points. So now the question is how we can define it in a mathematical way. Let us recall how we defined a usual random variable. So this is from what we can start. So when you study beginning of probability theory, you consider a random variable. And what is it? So you have some probability space. So this is omega, the set of all outcomes, and sigma algebra on it, and with some probability measure. And you define a random variable as a mapping from the probability space onto R. Yes, and we define this random variable of omega. So we have some value. But this mapping should not be just general, but it should be so-called measurable. So what does it mean? So in this case, we consider the space of values, so the line R with parallel sigma field on it. And to define a random variable, we should check that the preimage of any Borel set, so if I take any Borel set on real line, then the preimage, so what is it? This is all points of omega such that x of omega belongs to B. So this subsets of omega now should belong to sigma field F. So this is very important property that we should have in order to define a random variable. Yes, so for example, I take here B and I consider all points that are preimage of. Okay. But now, if we have the picture which is more complicated, we have a collection of random points in a space. How we can be sure that we will have such measurability in our case? So first of all, we should understand what is the so for point process. What is our mapping now? So we have the same, the probability space on one side, and we want to, for each omega, we want to put into the correspondence some random subset. Yes, so what is the space of this random collection? So we can, of course, we can, at first, we can consider, okay, let C, this will be the set of all countable subsets of our space. So let us write this. So I will consider sub sets of my space X, and such that X is countable or finite, or okay, so this is a space of all configurations. Okay, I can do this. And on the first step, of course, anyone can take omega and put into the correspondence some element in this space C. But how we can be sure that this mapping is measurable? So we should somehow define a set of sigma fields of a sigma field in this set C, as I denoted. But it turns out that we can find more fruitful approach in order to describe a point process. So how we can do this? So we will not consider a point process as a set of some finite or countable subsets, but what we can do here. So if we have such a mapping, we can put into the correspondence a family of measures. So what do I mean? So if I have some random configuration Z, and it depends on omega, I put into the correspondence measure I will denote by nu that depends on omega, and it depends on subset B. And I will define it as a number of points. So I will use this modulus, number of points in configuration Z of omega that belongs to subset B. So, and this value I will calculate for all subsets of B. So what I did now, I have space omega F. Then I put into a correspondence some random configuration Z of omega. So I have some configuration of points in my space X. But I will not consider this as a configuration of a points. I will do one more step, and I will consider the family of measures. So I take the any subset B, and I count the number of points that belongs to this set B. And you can see that if I have this set of values eta, then I can say everything about the configuration of points in X. Yes, you can. This is one-to-one, one-to-one mapping. So here, if I know eta from omega and B for all B, then you know everything about configuration of points in the space. So this gives us a very good idea how we can describe a collection of points in the space. So we will not think about a point process as a collection of points in the space, but we will consider a point process as this collection of measures. So let me write now that first know that for each omega small, for each omega, as a function of second variable, eta is a countable measure. So actually, it is supported. It is supported on the points of configuration zeta of omega. So now we consider that we can think about a point process as a random measure. And it turns out that this approach is most fruitful, and it is now the way to investigate point processes. So we consider it as a random measure. But for now, we did not say nothing about measurability. Okay, we now understand that we can describe a point process as a mapping from space omega into the, I will write space of measures. And since we have a number of points at most accountable, then measure will have values in natural number or zero or infinity. Yes, so we have such measures. So now let us define more precisely what is the space of such measures and how we can define the measurable structures on the space of measures in order to understand that this mapping is measurable. Is it measurable mapping or not? So let us give at first definition of a space of measures that we will consider. So let us start from the space where our points will live. So I have some space X with sigma field on it. Be a measurable space. And on this space, we will define the set of measures, and I will write sign my less than infinity on this space X. So for simplicity, I will not write this space X when it obvious. So what is it? This is a set of measures mu on X. So this means that these measures are defined on the sets of this sigma field, of course, such that for every set B in this sigma field, the value of B is natural or 0. So this is finite accountable measures on the space X. And now let us define the space of measures that we will consider. So just n, and define this. This is the set of measures that can be represented as sum at most countable number of measures. So if I have countable number of measures from n less than infinity, then I will have the my space of measures mu. Okay, so here please note that, for example, what kind of measures we can have in this space n. So let's consider examples. So the most simple example, of course, 0 measure that is just for every subset B, this is 0. Next simple but not so trivial example is called Dirac measure at point X. So this is just by the definition, this is indicator of let me write it, of some subset. This is indicator of set B that X that belongs to this set. So it is equal to 1 when X in subset B and 0 when X is not in B. Yes, so this is an example. And of course, if we have finite or infinite sum of delta measures, it will be again the measures. So if for sequence of points x n, and from 1 to infinity or a finite sequence. If I define measure mu as sum of Dirac measures at points xn, then I will have by definition, yes, by definition, this is such a representation. Then mu belongs to n, to set of measures. Of course, here we should note that if I have points that are the same for different indexes, if I have such case that I not is equal to y, then we will have the case when we have so-called weights in points. Yes, so how you can understand this Dirac measure, that at one point you have weight 1, but if you have here this summation equal points for the same for different indices, this means that you have several points, and for example mass will be bigger than 1. Here mass 1, so, but at some points it can be that the weight is more than 1, and in this case we will say that mu have multiplicities. So sometimes in some model it is useful to consider different weights for points. Sometimes it is useful to consider all points of mass 1. So this is just depends on the model that you consider. Okay, now we understand what is our space. Now let us think about what is the measurable structure can be here. And how we can think about it. Okay, let us assume that we know if we have random measure. I will take in brackets for now, because to define a random measure we should have already the sigma field. But if I have random measure eta so for all on one hand, B is subset of sigma field on our space. What kind of probabilities we would like to calculate? What we would like to know about this. So, of course, the first general and simple question we will have: what is the probability to have some number of points in some specific space or in some specific subset? So this is the general and most common question about how many points do we have here? What is the probability to have 2 points or 0 points? So we want to know such kind of values. So from this, now we can understand that we would like to know that this event belongs to sigma algebra on our initial probability space. So we should assume that our random measure has this property. So taking this in our mind, let us define the sigma algebra on the space of measures. So I will define right by n that is defined on space X, or just. So this is sigma algebra. So I will write the smallest sigma algebra that contains this subsets, this sets of measures. So let me write it. So this is all measures mu from set of measures such that mu from P is equal to K. So this, once more, I fix here subset B, I fix number K, and I consider all measures with this property. And now I can vary set B in sigma field X, and I vary all values K. I assume I know I use this notation, so this is all natural numbers plus 0. So I can construct the smallest sigma algebra that contains all such subsets of measures. And it turns out that such sigma, to consider such a sigma algebra is enough. And it is also useful to know that this sigma algebra n is also smallest sigma algebra such that the mapping if I will consider the mapping from mu into the value mu of B is measurable. So here, please note, so this mapping is from set n into natural number plus 0. Don't miss this letters, please. Okay, it is very simple to see because you just can consider this mapping is measurable if it belongs to such subset. So now we have space and we have sigma field on it. So we now can define to give the definition of random measure or of a point process. So this is the main definition of a point process. So a point process on X just is a random element in random element eta of space that we define n. So here, all measurability is hidden in this word, random element. So this means that we have measurable mapping eta mapping from omega to n is measurable. So all this talk was just about how we can define a measurable mapping. So we now understand the sense of these words, measurable mapping, because we have the definition of sigma field and on the space of measures. Okay, if we have this definition, let us consider example. And of course, the first example that we want to have, the most simple one is the following. If I have our space X is just R, and if I have a random point on R, so I have just the random variable. Let X be a random variable. So the question is, if I consider the Dirac measure at this point, will it be the point process or not? So, of course, we want that this will be the point process, but if we have the definition, we should check that this is indeed a random point process. So I write this eta is a point process. Let us first time just check it rigorously. So what is the event that eta of b is equal to some key? So in order to check that this is a point process, by definition, I should check that this set belongs to omega. I can write more precisely the points of omega such that eta, so we have two variables, is equal to k. So we can consider cases, and we will have cases k equal to 0, k is equal to 1, and otherwise. So if k is equal to 0, this means that x does not belong to b. This x is that x of omega does not belong to set b. In the case when k is equal to 1, we have the set of omega such that x of omega belongs to set b and empty. Otherwise, yes, the value cannot be bigger than 1. And obviously, since we know that x is a random variable, so we know this assumes that such subset belongs to sigma field F by the definition. Yes, I recall this definition of a random variable at the beginning. So we have this property. So indeed, for each set, so for each subset B on we have that this set on equal to K belongs to F. So the mapping is measurable, and indeed we will have a point process. Now, it is you can recall how you prove in the probability theory that the sum of random variable is again a random variable. So we will have automatically the next example. If I have the set of x1, x2, and so on, random variables, then if I consider eta, which is equal to sum of delta measures at points xi, then this will be again a point process. Point process. Now let us consider an example that is some partial case of this general example, and we will use sometimes this process. This is so-called binomial process. Binomial process. On the previous lecture, we considered just binomial distribution, but now we are talking about binomial process. So to define a binomial process, we should fix two parameters. One of it is the m. This will be the total number of points in whole configuration. So this is a number of points m. And we will fix the probability distribution. I will denote it by Q is a probability distribution. Probability distribution on our space where we consider this point process. So this will be space X, or if it is more simple, you can consider here R. It's up to you. And I consider now not general but independent random variables from 1 to m. They will be independently identically distributed random variables with distribution Q. And now if I define the, as in my example here, from 1 to m, delta measures at points xi. Why is it called binomial process? Because if now we will try to calculate the probability that we have at set B exactly k points. So I fix, let me draw a picture here. So this is all my space X, and I have here m points. Yes, this means that I have m points, and I consider subset B. And I want to calculate the probability that I have exactly k points in this subset B. What should I do? First, I should choose this k points of a total number m. So I write combinatorial binomial coefficient. And the probability that a point belongs to the set B is equal to this distribution. So I just write the distribution of this subset B into the power k. So I have k points in set B, and other do not belongs to set B, so they belongs to a complement of it. So I have into the power m minus k. So since we have such expressions for probabilities, from this we call this process a binomial process. Please note that here the distribution of the points can be arbitrary. We just now talk about the whole subsets or configurations of points. So here you can see this binomial distribution. Okay, so this is the case, and one more words about the examples. So here, as you see, I give you examples of measures. So here, when we discussed a measure of the space that we considered, we always talk about such kind of examples where measure can be defined, can be represented as sum of Dirac measures, but this is not the general case. Of course, these examples of measures were very general one, but if you are interested, you can try to construct the measure mu that is not represented in such way. So this is an interesting example. And in this, with this in mind, we can assume that there exists a point process that cannot be represented in such way when we just put random points, random variables, and just consider them as a sum of delta measures. So, but this kind of processes is quite general. So for them, we have some notion. Let me write it as a definition. So this is so-called proper point process. So a point process eta on space X is called to be a proper point process. Proper point process. If we can find the sequence of random variables x1, x2, random variables, random elements in X. And here, of course, we do not know the total number of points in the space. So here we also can vary the number of total points. And we can do this just considering the random variable kappa. Okay. Random variable kappa with values or natural number or 0 or infinity. valued random variable. So if there exists such object such that we can represent a point process eta as sum of delta measures at points xi, where I is from 1 to kappa. So please note that here the number of summands is random. I can write here omega. In such way. So this is proper processes, and mostly we will have the case with such processes, but it is interesting if you can give me an example of a point process that is not a proper point process. So this is like exercise or work exercise. Give an example of not proper point process. So this means that we cannot consider it like just the points in a space, yes, because this representation just as we understand a point process like the set of random points in the space. Yes, but it turns out that there are some cases when we cannot give such representation. Okay, but this is more the rather big class of processes. Okay, now let us consider some properties of a point process, and we can write down such a subsection of this lecture is a Campbell formula. Campbell's formula. So if we have a random process, we want to know some characteristic of it. And when you studied random variables in probability theory, you of course you first studied the distribution function of a random variable, but now we will do it a little bit later. But the most easiest what we can do about a point process is to study it first moment. So this is the first characteristic, and let us give this definition. But now if I consider a moment of a random measure, we will have not a number like in a case of a random variable, but we will have a measure in the answer. So this is called the intensity measure. Intensity measure. Lambda of a point process. Point process. Eta is the measure that is defined by the formula. So I just write the expectation of number of elements in a subset B. Here. Yes. And here I stress that this is the measure, And this is like a very easy exercise for you. Exercise or check, just recall what property should have the measure in order to be called a measure. So check all properties in the definition of a measure. For lambda. Yes, so we have this object lambda. It is defined on subsets B. And I just want to be sure that this is indeed the measure. And the most, let us consider example. So if I have a binomial process, as in previous example, so this means that I have the sum of delta measures, and I want to calculate its intensity measure. So I write expectation, and here sum k from 1 to m. So let me write here the parameters m and probability distribution q. And here delta measure I can write as indicator of set B of point x k. So I change the order, and this is the sum of probabilities that x k belongs to B. And since I have this probability measure for the distribution of x, and I have the m equals a month, so this is the intensity measure of binomial process. Okay. And now let us consider the Campbell formula. This formula generalizes the example that we considered. What do I mean? So at first, if I have a random measure, of course, we can consider the integral with respect to this random measure. With respect to random measure. So we can consider it with respect to any measure. So if I have a function, let me write u is a function from u from x our space into R. Then I can consider integral. Sometimes I will denote it by such brackets. So this is just by definition integral on the set x u of x nu dx. Please do not be afraid of such integral, because, for example, if we have a nu of the form delta measures, what is the form of such integral? Integral of x nu dx. What is this? So this
is a sum?
Yes, this is just the sum. Sum at this random points. So when we have a proper point process, this is very simple to understand what is the integral. And this is an example of the most general class of linear functionals that we will consider later with point process. And the Campbell formula states the value for expectation of such integral. So this is a theorem. Campbell formula. This is easy to prove, but let us give the statement. So let eta be a point process on space X with intensity measure lambda. So we know some information about it. And let u be a function from set x into x. Then, into R, I'm sorry, into R. Then the integral mu dx is a random variable, and this means that we can find this expectation, and expectation of the integral mu dx is equal just integral of the same function, but with respect to intensity measure. So you see, if you have here just some integral of the form that we have here, just summation, maybe of a such form, but on the right-hand side, we will have just integral, and in some cases it is not a summation, because in general case, lambda is not the sum of delta functions. So, and this is true whenever u is positive, or we should know that this u is integrable absolutely integrable with respect to measure lambda. And for the proof, it is not hard to see, and maybe this is so the first step, just to consider the simplest functions that we can imagine. We just take the indicator of some set B. So that is equal to 0, 1. And then what is the integral of such measure? This is just the value of the measure nu of the subset B. And of course, if you write the expectation of such function, such a random variable, of course this is a random variable. And of course, this is equal to expectation of B. And by the definition, this is the value of measure lambda. Now the next step, we use the linearity of expectation. In order to have the formula, we will have the formula for functions of the form u of x is equal just some constants ak, indicator bk of x, k from 1 to n. So you will have just and the third step, we use approximation. We use step functions approximation for non-negative u. Yes, I think that this is a common approach. I will not give here details. And the step 4, just to represent the function u as difference of positive part of it and negative part. So where here u plus is maximum of u and 0, and u minus is maximum of minus u. So here the known steps how we can use approximation and then split into positive and negative parts. So these steps proves us the Campbell formula, and now we can see how we can know if we know the intensity measure of a point process, we can find at least expectation of all such linear functionals of the point process. Okay, so that's all for today's lecture, and if you have some questions or comments, you can ask.